Section 12.2 is on the Two-Way Anova. And in order for us to run a Two-Way Anova, we need to look at an interaction between the column and row variables. And the interaction between those two variables is if the effect of one of the factors changes for different categories of the other factor. We could create an interaction graph by calculating the mean for each cell of a two-way table and then construct its graph. And based on this graph, if there is an interaction effect, that's suggested when line segments are far from being parallel, and there's no interaction effect if the line segments are approximately parallel. This picture is an example of a no interaction effect, even though these definitely don't look parallel per se, but they're parallel in the sense of they're not going to intersect, based upon the way that this graph specifically looks. And the two-way analysis of variance, or Two-Way Anova, is used with sample data categorized with two factors, a row variable and a column variable. We would first test for an effect from an interaction between the row factor and the column factor. If there is no interaction, we then test for an effect with the row variable or factor, and then test for an effect from the column variable or factor. The requirements for this Two-Way Anova. We first want for each cell, the sample values must come from a population with a distribution that's approximately normal. And the procedure, though, is indeed robust against reasonable departures from normality. The populations have the same variance or standard deviation. This procedure, again, is robust against reasonable departures from the equal variances. The samples are simple random samples of quantitative data. These samples are independent of each other. Sample values are categorized two ways. These cells have the same number of sample values, which is also referred to as a balanced design, so they have the same sample sizes. And we want to first test for the interaction effect, with the null hypothesis that there is no interaction between the two factors, and the alternative that there is an interaction between the two variables. SAS gives us the p-value and test statistic f being the mean squared of the interaction divided by the mean squared error. The p-value of less than or equal to 0.05, which will be small in this case. We reject the null hypothesis of no interaction. So we say that there is an interaction effect. If the p-value is greater than 0.05, it's large, and we fail to reject the null hypothesis of no interaction, where we could say there is no interaction effect. And then based upon that, if there is no interaction, we then test for the row factor, where the null hypothesis of no effect from the row factor, where the row values are from populations with the same mean. SAS will give us again the p-value and the test statistic f of mean squared row divided by mean squared error. The p-value, less than or equal to 0.05, so small, is where we reject the null hypothesis of no effect from the row factor and conclude that there is an effect from the row factor. A p-value of greater than 0.05, so large, we failed to reject the null hypothesis of no effect from the row factor, and then we could then conclude that there is no effect from the row factor. To test for the column factor, again presuming that there's no interaction, with the null hypothesis of no effects from the column factor, so the column values are from the populations with the same mean, SAS will give us the p-value and test statistic f of mean squared column divided by mean squared error, and the p-value of less than or equal to 0.05, so small, we reject the null hypothesis of no effect from the column factor and conclude that there is an effect from the column factor. A p-value of greater than 0.05, large, we fail to reject the null hypothesis of no effect from the column factor and conclude that there is indeed no effect from the column factor. So, based upon that, we would, start our Two-Way Anova process. We test for an interaction between the two factors, and use a p-value for the test statistic of f of ms interaction divided by ms error. If the p-value is small, such as less than 0.05, we conclude that there is an interaction effect. So because of that, we reject the null hypothesis of no interaction, and then we stop after that. If there is no interaction, or we fail to reject the null hypothesis, then we test for an effect from the rho factor using the p-value for the test statistic f of ms rho factor over ms error. If the p-value is small, such as less than 0.05, conclude that there is an effect from the rho factor, and then we could test the effect from the column factor using the p-value for the test statistic f is equal to ms column factor divided by ms error. If the p-value is small, so less than 0.05, conclude that there is an effect from the column factor. So for example, given this table down here, from the data table 1 by data set, we want to use the two-way Anova procedure to test for an interaction effect, an effect from the rho factor of age bracket, and an effect from the column factor of gender at the 5% level of significance. And in SAS, I already have this data in here, but we would need to code it something such as this. We will list out each age and gender and list out each pulse rate from that. So unfortunately, we wouldn't be able to code it exactly the same way the table is down here. But I would put that into SAS. And the program that we need to use for this is proc Anova. Data is equal to whatever the data set is, in my case work.pulse rate. The class is going to be both the age and the gender, since those are our row and column factors. Age and gender. Model pulse rate, which is each of these values. Pulse rate is equal to age, space, gender, space, then the interaction is age, asterisk, gender. And then we would want to do means, age, space, gender. So then that way we can look at the to determine if these appear to be approximately normal and all that. So when we run this code, it will take its daily time. And in this case, not giving me what I'm looking for. Let me rerun that. And it is giving me a lovely looking error. Why is that? Let us see. Statement is not valid or used out of proper order. It's telling me that's line. There we go now. For some reason it doesn't like it when you leave things selected on the screen. But once it actually does indeed work, as it just did for my sake, we could see that these box plots do appear to be approximately normal. There's a little bit of variation, but we could say that these are indeed approximately normal for our requirements. So approximately normal. The second one about the variances, based upon this actual coding, unfortunately, SAS does not give us the specific variances, although it does give us standard deviations, which we could certainly calculate. But you could probably tell by just looking at some of these standard deviations, they vary a lot, unfortunately. So the variances differ substantially. the variances differ. Despite that fact, we're going to still proceed as normal, despite that fact. The third part is that we could assume that this is a simple random sample. The fourth being that these samples are independent. Mostly because, well, I mean, the two genders themselves are independent, and you can't possibly be in more than one age bracket. So, they're independent. We could see that the data is categorized two ways, based upon the age and gender. So, categorized two ways. And then finally, all cells have to have the same number of samples. In this case, all cells have 10 samples. So all cells have 10 samples. So we're first going to look at the interaction. We're going to first look at the interaction between these two variables. So for this, we are having the null hypothesis of no interaction, and the alternative of there being an interaction. And so we look at our code from SAS over here. So the interaction term is this last one on here, the age asterisk gender. This has a p-value of 0.3973. And because it is indeed so large, right, that's much greater than 5%, we would then say that there is no interaction. We fail to reject that null hypothesis. So there's no interaction. And now because there's no interaction, we are now going to go to let's do the row variable. The null hypothesis from this row variable is that there's no effect from the row variable. There's no effect. Alternative is that there is an effect. The p-value from this, when we look at SAS, is going to be this top row age of 0.1725. Again, that's greater than 5%, so there's no row effect. And again, because we have no interaction, we can now do the column effect. Again, the null hypothesis is that there's no effect based upon that column. The alternative being that there is an effect based on that column variable. The p-value that we get, looking at SAS code, is 0.0005. So a total of 3 zeros before that 5. And that's very small, right? So because of this, we can indeed say that there is a there is a column effect. So it's affected by gender. So there is a column effect. So the pulse rate is impacted by gender, according to our analysis. Let me know if you have any questions or concerns. Thank you.